Hey, welcome guys. Yeah, so this is my final lecture about analytic number theory, and we are in the previous two video that we have proved the Dirichlet series, the Dirichlet theorem. So there are infinite primes of Archimedes not Archimedes, sorry, there are infinite primes of the form like the Pn plus Qn plus a if GCD of Qa is 1. Okay, and our I think our final results boils down to the Dirichlet series. Okay, so you can check out my previous video, but finally our results based on the Dirichlet series, and our goal is to show. So the remaining goal is to show this strange fact that if somebody gives you the L chi of S that you define to be chi of n to S and from 1 to infinity, this Dirichlet series S is analytic. This is what we already proved. It's analytic when chi is a non-principal. Okay, but in order to prove the Dirichlet series, we need to take a log of this. Okay, so the final results, the final lemma, which is not simple, is to prove that when chi is not trivial, that the L chi of 1 is non-zero. Okay. Okay, so this is one. The reason is that we need to take the limit. Okay, so this is the non-trivial part, right? If you take S, I mean, you already know these guys. You already know these guys is non. You already know these guys well defined when chi is non-chi 0. But we need to ask, what is the one? What's the point? What if I take S, go to 1, whether it's non-zero? Okay, so this is our goal. Okay, so this is the difficult part. And okay, so let's do a simple lemma. Okay, so this is what we are trying to prove. Okay. Okay, so consider this P of S, where so you fix Q, and then you consider all the products of this all the character, and then consider this L chi S. Okay. And I want to claim that when let's say real S is sigma, I want to claim that if you plug S to be a real number greater or equal to 1 for sigma greater than 1. Proof. Okay, so idea is that you take a log of P sigma, and you can check that it become all the chi and all the P, and the log of this 1 minus chi of P inverse. Okay, so this is the Euler product of the Dirichlet. And just do a simple calculation that you can get the results like this. Or the chi to the P to the M. Okay, now you can check this guy, chi to the P to the M over chi will be the 5Q and 0 else. This is P to the M 1 equals to 1 mod Q. Okay, because the reason is that this sum over chi will be chi of P to M. Okay, so this is, you can use the group representation to prove this. Okay, but actually you don't need to worry, right? Because this guy is always positive. Okay, so this guy is always positive. Greater or equal to 0. So which tell you that this P of sigma must be greater or equal to 1. Okay, so proof is done. Very simple. Okay. Okay, so now we can prove our original lemma. We can prove this lemma. Okay, so we first prove the restricted one. So this is so let's say when chi is not trivial and the chi is complex. Okay, so all complex means that if you take chi bar will be another character which is different from chi. Okay, so for this one that we are very simple, right? Because I can write P of sigma as the Dirichlet series of the chi and S and the chi bar and S and the chi trivial S and the rest. So this is our chi do not the same as chi by notation. Notation is terrible. Okay, so let me just change this. Let's say let's use it. Let's say chi1. Okay, so it's 1 and 1. Okay, so consider chi1 is a complex character which is non-trivial. So I do this chi1, chi1, chi0, and then not chi1, and then also not chi1 bar, and the L of chi of S. Okay. Okay. So this is, let's say this is Q of sigma. Okay. So notice what? So so from here. So okay, so first I know that this guy will blows up, right? These guys are just the same as theta function. So I know that this L of chi0 S will approach to, if I put real S to be sigma, this guy will blows up. So it will be 1 over sigma minus 1. Okay. So something like big O of 1 over sigma minus 1. And let's prove by contradiction. So prove by contradiction, I suppose that L chi1 of 1 is a 0. Okay, so this means that since this is a continuous function, so which tell you that L chi1 of 1 will be O of sigma minus 1. Okay, well, when sigma approach to 1, it becomes 0, right? So it's bounded by sigma minus 1. Okay, but then you can easily show that L of chi1 1 will be the same as L of chi1 bar 1. Okay, so very simple exercise that you can just check it, because you can take a conjugate of the series and then you can prove this. If they are 0, right, then this will also be 0. So this gives you that L chi1 bar 1 will be O of sigma minus 1. Okay, but this, okay, so consider this one, and this one. This one will make the P of sigma to be sigma minus 1 big O, right? Because there are 3 terms. So it will be sigma minus 1 square delete, right? So get O of sigma minus 1 times the rest of product. Okay, the rest of product is bounded for fixed Q. So this die goes to 0 as sigma goes to 1. Okay, but this violate our results, right? Because as sigma goes to 1, at the previous that we proved that P of sigma should be greater or equal to P of sigma should be greater or equal to 1. Okay, but we proved that the P of sigma will goes to 0 as sigma goes to 1. So this is contradiction. Okay, so that means for complex character that this proof is very good. Okay, but the problem is that if now chi is a real character means that for every input is real. Then for a real character, that you can see that you only get 1 terms. If you want to follow this proof, then you only get 1 terms. So you cannot use simple proof to prove when chi is real. Okay. So this is our final part. Okay, so this is our goal theorem. So when chi is real, we still have the results. Okay, so this proof is very long, so very hard, very detailed. So I don't want to do step by step, but I will sketch the proof. Okay, so you can check the following. So let's say the simple lemma. So lemma is this. So f of n, if you define f of n, let's say n is an integer. Let's say n is square. If n is square, then you says you define sorry, it's okay. So let's consider this. So lemma says that if chi is real, and then we define a Dirichlet let's say f defined to be chi Dirichlet product with the identity, then the f of n is greater or equal to 1 if n is square, else is 0. Else you can only prove that n is greater or equal to 0. Okay, so this is a very simple proof. So proof is that we know that chi is multiplicative. Okay, so since chi is multiplicative, right? So we know that f is also multiplicative. Okay, and the chi is real. Okay, so chi is the root of unity. So chi of p can only be plus or minus 1 if p and q are coprime. Okay. Okay. So which gives you the following. So if you compute f of p to the m, let's say pq is coprime, then you get 1 plus chi of p to the k for k from 1 to m. Okay, so this is the definition that you get 1, right? If p if p divides q, then the character will be 0. Okay, so it's 1. If p do not divide q, then let's say chi of p is 1, then it's 1, 1, 1, right? So it's n plus 1. Okay. So if p divides q and chi of p is minus 1, then you get minus 1 to the k, which is even 0 if m is even. Okay, so if m is odd and the chi of p is minus 1 and the p do not divide q, then you get 1. Sorry, I'm stupid. This is m is odd. This is m is even. Okay, because it's odd, then this guy will give you a minus 1, so you get 0. If it's even, then you get 0. This guy will give you 1. Okay. Okay, so we prove our results, right? Because this tell you that f of p to m greater or equal to 1 if m is even. Okay, if m is odd, then you can only say greater or equal to 0. Okay. Okay, so this is the first theorem, first lemma. Okay, the second lemma. The second lemma is this. If you sum 1 over square root of n and n less equal to x is 2 square root of x plus a constant plus big O of 1 over square root of x. And the proof is very simple, just using the partial integration or basically summation into the series, so Euler formula. Okay, so proof skip because this is trivial. Okay, so you should be able to just do 1 over square root of x and then do the integration, then get the first part and the remaining part is bounded by this. Okay. Okay. Let's say there's a third lemma. Okay, so now you see this theorem is very difficult to prove. Okay, so we take this. Okay, and let's say chi is non-zero. Sorry, not principle that you can. I mean, this is definition, right? So this is this. But let's say you only to do the partial sum, right? You only do a partial sum, so you change this to be n less or equal to x. So you get this and the arrow turn, and the arrow turn is dependent on q and s, but bounded by 1 over x sigma. Okay, so x greater or equal to 1. This is very simple that you can easily prove. Okay. Okay, so now we have everything that we can start to prove our theorem. Okay, so now let's consider is s of x defined to be summation of fn, that's a square root of n, and that's equal to x. Okay. So you can write s of x in terms of okay, so first we notice that if we take the only square term, and since f is square term equals 0, right? So if I take only square term, let's say I consider m squared less or equal to x, and the f of m squared, square root of m squared, I get the summation of n greater or equal to square root of x. By definition, when m is because this guy is square, so this square root equal 1 over square root of m squared, so it's square m greater or equal to x square root of x over m. And then this is log x, right? So log square root of x. Okay, so it's half log of x. Okay, so this just show the s of x is lower bound is log of x. So s of x cannot be decreased faster than log x because it's bounded bounded below. Okay, so now let's consider the upper bound, or basically we try to try to prove there's a contradiction. Okay, if we assume that the character of, so our goal is to prove that L chi1 is non-zero for real chi. This is our goal. Okay, so another direction, let's consider s of x. Consider dm that's equal to x, dm that's equal to x. So we just write it down, right? So we separate in terms of the definition of f. Okay, so let's write it as sigma 1 plus sigma 2 minus sigma 3. So sigma 1 is d that's equal to square root of x, chi of d square root of d, m that's equal to x divided by d 1 over square root of m, and also chi 2, m that's equal to square root of x 1 over square root of m, and d that's equal to x divided by m, chi of d square root of d, and also sigma 3, which is a summation of chi divided by d square root of d, d that's equal to square root of x times 1 over square root of m, and that's equal to square root of x. Okay, so you can just prove this by a simple calculation, just separate into two terms. Okay, so our goal is to show that if you assume that this guy is 1, basically if you assume that this guy is 0, then you get contradiction. Okay, so let's quickly do this. Okay, so very simple calculation that so sigma 1 will be, you can prove this will be 2 square root of x L chi 1 plus O1. Okay, this guy you can prove. This guy you just do the same thing, right? You can I think. Okay, so let me just skip the detail. Or you can try to prove this guy will be L chi half 2x over 4 plus O1. And then the final this guy will be L chi half 2x over 4 plus O1. Which you combine everything, that you can prove that s of x is 2 square root of x L chi 1 plus O1. Okay, then right, now if you say this guy is 0, then you prove s of x is O1. Okay, but this violates log x. This violate we first proved that this is log x. Okay, so this is very non-trivial proof that you come up with 2, and you can check that this guy is actually the same as this. Then this violate all your formula. Okay, so this is the final ingredient of this Dirichlet theorem. So let me just final recap. Okay, so idea is to show the idea of the previous idea of these 3 lectures to prove that let's say P is A mod Q. You want to prove that this P is A mod Q somewhere where P will blow up, right? So our final results will be this is 1 over 5Q log x. Okay, and actually there are higher mathematics can try to understand this error term. This is very difficult, but this is our goal. Okay, and our goal to prove this is to connect this to the L function. So the idea is that you can start from the L function. Okay, and you use the orthogonality, right? So simple idea is that you take say, let's say you take some orthogonality, you take this guy, do using the orthogonality to do things, and then use sum over chi and use sum over chi. Okay, and the orthogonality will give you a lot of terms. One is the principal character terms, which you already know it will blows up, and the rest term will corresponding to some log of original L as chi, for chi is non-character. Okay, so so this is why we need to prove that when s goes to 0, then this guy is finite. When this guy is finite, then this guy is infinite by direct computation. So you can prove that this guy must be infinite. So which give you this kind of results. Okay, so this is like we spend like the 1 hour to prove the detail and highlight why this dirichlet theorem is true. But this is, I think, a very interesting idea in a number theory. See you guys next videos.